So you may recall we said that every one parameter Lie group of transformations, let's suppose it is given by the map star, which acts on, so you've got your parameter coming from your Lie group, one parameter Lie group, acting on an element of the manifold to give you another element of the manifold, like so. It turns, well, we said that the tangent vectors may be represented in vector fields, in vector field form. So equivalently, the tangent vectors to the curves generated by the one parameter Lie group of transformations have the form xi d dx if it's in two variables, x and y, eta d dy. Xi and eta could be functions of x and y, where we showed that xi was dx bar by dg, g being the parameter, at g equal to 0, and eta is the derivative of y bar with respect to g, the parameter evaluated at g equal to 0. We may notice here that x bar, if you do an expansion, since x bar is a function of x, y, and the parameter g, if you expand that around x, this can be written as x plus g, the derivative of x bar with respect to g at g equal to 0, plus higher powers of g. This is equal to x plus g. The dx bar by dg at g equal to 0 is in fact xi, and this is the same xi that features in the vector field. And similarly, we can show that y bar up to order 1 in g can be written as y plus g times eta, and then of course higher powers of the parameter. So the vector field, the tangents that represent the one parameter Lie group of transformation, have these coefficients xi and eta featured as coefficients of g. And keep this in mind, the coefficients of g in the expansion of x bar or y bar gives us xi and eta, which feature in the vector fields respectively. So one needs to keep in mind of these various forms of, first of all, the one parameter Lie groups of transformations and the vector fields that represent the tangent vectors to the curves generated by the one parameter Lie group of transformations. Okay. Now, an important aspect of invariance and transformation theory is identifying functions that are left invariant under a change of variable. The change of variable in our case is generated by the one parameter Lie group of transformations. For example, the xy's, and remember this could be xyz or x1, x2, etc., is transformed to x bar, y bar by the map star, and of course the parameter g. So the definition says that a function of x and y is invariant, form invariant, right, under a one parameter Lie group of transformations generated by star. So let's say g star on xy, that is our one parameter Lie group of transformations, if of course f of x bar y bar is the same as f of xy. So our example that we've been using, the rotation example, the one parameter Lie group of transformations that generate rotation, recall. So let's look at that as an example. So the example is, let's suppose G star on xy is given by x bar y bar, where x bar is the old classic example of ours, x cosine g minus y sine g, and y bar is given by x sine g plus y cosine g. That is x bar, this is y bar. Right, then if you take f of x bar, well, then let f equal x squared plus y squared as an example. From this we get that if we determine f of x bar y, this is f of xy, f of x bar y bar will then be equal to x bar squared plus y bar squared, and this is of course the x bar y bar that is featured in G star x, x bar being x cosine g minus y sine g, and of course the y bar is x sine g plus y cos g, etc. If you do the multiplication here, you get x squared cos squared g, etc., etc. And if you simplify this, you end up with x squared plus y squared, and that is equal to f of xy. So therefore, this function f is invariant, is left invariant by this one parameter Lie group of transformation, by this one parameter Lie group of transformations. We have a theorem that says the following, that the functions that are left invariant under a one parameter Lie group of transformations are annihilated by the corresponding vector field of that one parameter Lie group of transformations. So if the vector field x is equal to, say, x dx plus eta dy is the tangent vectors, is the vector field, tangent vectors of a one parameter Lie group of transformation given by G star xy, then a function f is invariant under this one parameter Lie group of transformation so under the one parameter, this one parameter Lie group of transformation, if and only if the vector field x acting on f is equal to 0. So here's an alternative way of checking whether a function is invariant under a given vector field. So in the above example of rotation, right, the vector field, the tangent vectors, are given by xi is y, so it's y d dx, and eta is x, so it's minus x d dy. So this is the vector field corresponding to the one parameter Lie group of transformation above. Then the vector field x on the function f above is x on x squared plus y squared, and now we treat the d dx dy as your classic partial derivatives. So this is, if you act the vector field x on x squared, you get y d dx of the bracket is 2x minus x, the d dy of the bracket is 2y, and this is equal to 0. This confirms the result. So there's two ways of checking if a function is invariant. One is to check the definition, by definition, and the other is to check whether the vector field on that function is equal to 0. The good thing about this theorem, or the nice thing about this theorem, is that we can use the theorem to identify all functions left invariant under a one parameter Lie group of transformations. So let's look at the following example, where we might say find all functions f of xy that are invariant under the one parameter Lie group of transformation. Let's look at the same example, the one with the cosines and the sines, where g star on xy gives us x bar y bar, and that's the same example I'm looking at above. Okay. So again, the vector field here is the same vector field. The vector field x is, of course here f is the unknown. This is x d by dx minus y d, this is d dx minus x d dy. This is the vector field corresponding to that one parameter Lie group of transformation. Right. So if a function f is invariant under x, then since f is unknown, we need to solve for that. So then let x on f equal to 0, and then solve for f, i.e. this will then be y df dx minus x df dy equals 0, and we solve for f in this first order linear partial differential equation. And we use a classic method of characteristics, where we find invariance and then write down the result. So in characteristic form, this reduces to, or can be written as, solving this system of ODEs. We have a dx over y that comes from that dx and y equals a dy over minus x, and this equals df over this 0. Sometimes that is non-zero, but in this case it's 0. What this over 0 means is that that f there is itself an invariant. Just keep that in mind. Now, we use the system of ODEs, which of course in the case of more than two variables xy, if we have three variables x, y, and z, we'd have another ODE. So we use this set of ODEs to determine the integration constant. Each integration constant serves as an independent invariant. So here we have just two independent variables, namely x and y. So we only need one independent invariant. So from here, if you do cross multiplication, etc., you find that you get minus dx equals y dy, and if you integrate, etc., you find that an integration constant is x squared plus y squared. This is then an independent invariant. Like I said, that if there was a third variable z, we would have to find a second invariant. So for n independent variables, we will need n minus 1 integration constants, which will serve as n minus 1 independent invariants. We use this differential, and usually we'll pair it with one of those to construct another integration constant, but that integration constant will be a dependent invariant dependent on the independent invariants. But in this case, we don't have that, and we have the simple case that since df is over 0, so from that df over 0, f itself is an invariant but a dependent one. So f is a dependent invariant. Let's say gamma equals f. So gamma is your dependent invariant. And gamma, being a dependent invariant, is some arbitrary function of the independent invariance, which in this case is just alpha, i.e. your function f, gamma is f, is an arbitrary function of alpha. Alpha is x squared plus y squared. So any arbitrary function of x squared plus y squared is an invariant of this one parameter Lie group of transformation indicated here. So essentially we used the theorem to determine that. Keep in mind that if you have 3 independent variables, so I will do part of such an example. So suppose we have another example where we are given the one parameter Lie group of transformation in the vector field form. If you don't have the vector field form, you have to find the vector field form to use the theorem. So suppose the vector field is the scaling transformation given by, suppose, x dx plus 2y dy minus z dz. To find the functions left invariant under this vector field, so all functions, this time of 3 variables, invariant under this x, satisfy x on f equal to 0, i.e. you've got x df dx plus 2y df dy minus z df dz equals 0, and therefore if you write it in characteristic form, you got dx over x equals dy over 2y equals dz over minus z. So this system of ODEs will, since we have 3 independent variables, will give rise to 2 independent invariants, and of course we'll have to find a dependent invariant coming from df over this 0 there. So you would solve, say, these 2 to give you alpha. You would solve either this 2 or those 2 to give you another independent invariant beta. From this we have a dependent invariant given by gamma. Gamma will be just very simply f, since df is over 0. And gamma, of course, is going to be an arbitrary function of alpha and beta, from which, of course, you would substitute the forms. Gamma will be f, alpha will be whatever it is in terms of x and y, beta is whatever it would be in terms of either xz or yz.